So any questions about homework? Lab 1, yes?
I believe it's the question in homework 1, it asks you to explain the components which connect to a few specific pins.
Yes.
So for example, this one pin called VCC and it's connected to a parent of like power regulator. Then we just simply say it's a power regulator like.
But it's also, yes, so VCC on the chip is connected to the power regulator and to 2 bypass capacitors to ground.
Yeah.
So what do?
Yeah.
Anybody?
Decoupling faster than filtering it?
They're decoupling, which means that fast current transitions in the chip do not require fast current transitions in the power supply. Rather, the capacitor supplies the charge. Anything else? Any other questions about homework 1?
Does Hapsim run at a slower in real-time rate?
Does what?
Hapsim, the LED simulator, LCD simulator you put on the website.
Hapsim, I have no idea.
Okay.
I've never used it.
Running a lot slower.
Oh, I wouldn't doubt that it runs slower than you'd expect. Yeah, there's a couple of this is a cycle accurate simulator, right? Yeah, I tend not to use simulators because the boards are so easy to come by. But I understand that that's my limited viewpoint, not necessarily for everybody. Anything else about Lab 1? I have a comment. Yes?
And also for the LED question, so does that mean we just go randomly online to find a spec sheet for red LED?
Well, random is not quite the right word. I would say Google up voltage drop red LED.
No, I mean, but for that red LED, it's a kind of random one because I'm assuming there will be some variation when it comes with.
Yes, there will be some variation in the turn-on voltage, and like any diode, it has a voltage at which the current starts to get large, and that's the voltage beyond which you can't go. And the dispersion for red LEDs is, anybody have a feeling for the turn-on voltage of a red LED? About 2 volts. Plus or minus 0.1. Depends on the wavelength. Green, 2.5 volts. Blue, 2.6, 3. Ultraviolet, 2.9. Yeah, it's about, actually it's about 4. It's about 4 volts, 3.9, 4 volts. So you will find that because there's a certain, the diode can take 25 mils or 18 mils, that I'm not asking for an exact number. I'm not asking for 4 decimal places here. I'm asking for 1 decimal place in how you do the current limiting. Lab 1 has one small trick that probably some of you have detected. One is there's a state which I'll call ready, where the LCD is saying ready, and there's a transition to the next state. This is not a state transition diagram, but there's a push button that takes it to the next state, which is a wait state. A wait state. And the transition to the next state is 1 to 2 seconds randomly, at which time an LED and a buzzer come on and the lights flash and so on. And then the human has to push a button, and then after the human has pushed the button, their reaction time is displayed. And then when the human pushes a button again, you go back to the ready state, right? And that's the specification for the lab, and it's always supposed to be the same button. Now, so you press ready here, you're in the ready state, you push the button, you release it. If you hold down the button for more than 1 or 2 seconds, it really goes off into another state, which is cheat. But So there's no problem. You push and release the button. Now, the LED comes on. You push the button. You get the displayed time. You're holding down the button. Uh-oh, the button's pushed. It drops back to ready. Therefore, after this push, you must debounce. Right? You must detect a button up before you're allowed to have another button down. So there has to be a release on the button. There has to be a push. It has to be released before this push can be valid. Does everybody, you get that? Now, the thing which makes this interesting is that mechanical buttons all bounce. They're spring mass systems. They oscillate. So when you push a button, you think the voltage should do this, but in fact, it does this. And it can pass the CMOS transition voltage n times in about 15 to 30 milliseconds or so. So you push the button, you push this button, you detect that it's come back up, but it's still bouncing. It hits again, and it falls through the loop, and you never see the displayed time. So you have to detect not only that the button is released, but that it stays released for 30 milliseconds. Suggests a state machine. Have you done this in another course? Did you do this in 3140? Debounce? So you've seen debounce state machines. I'll do one later on in any case, because some of you may not have seen it. But you must debounce these two pushes. You can't debounce. You must not debounce the button down here. Because if you were to say, first strike of the button is here, but it settles here, then you would have decreased the reaction time of the human by an artificial 30 milliseconds. So here, for this button push, you have to take the first bounce of the button as the button down time. Any questions on that? Okay. And generally, solutions to these programming problems that require lightning fast reflexes and twitching on the button at just the right rate won't be acceptable. It has to be operatable by a normal human being. So let's see. I think I was in the middle of a code. Yes?
Just one more question about the lab. So based on the lab manual, it seems we are going to use the SKT500 board, right?
Correct. STK500.
But on the homework, we are also looking at the protoboard design page, which seems that one seems to has like part of functionality which an SKT500 has, right? But that's just kind of doing it yourself, right?
Right. The prototype page, prototype board page, is a piece of the STK500 which is meant to be built into something else. Or the STK500 is this big, and you wouldn't want to build it into stuff. And besides, I wouldn't let you because it cost $80. But the target boards, these that are on the prototype board page, you will each have a chance to build if you want to, and if you build one, it's yours.
Okay.
So, for final projects, or even before final projects, let's say that you want to buy an oscilloscope for home, for your dorm room or wherever. You want to buy an oscilloscope and a programmer, but you don't want to buy an STK500 board. Then you could build a prototype board and take it home and program it and do the labs that way. Nothing else leaves the lab, though. No LCD displays, nothing else. You'd have to buy all of that for home. But you're welcome to build a prototype board as soon as you want. I have all the parts for them. If you want to get going on surface mount soldering. How many people have done surface mount soldering? All right. All right. These are TSSOP, which is 0.025 inches on center for the leads, and they're moderately easy to do under a microscope, which I have there, and with a fine tip soldering iron, which I have until somebody drops them on the floor, which happens 5 times a semester. So I think they're still good from last year, but I'll check. The reason I linked up that page for homework 1 is, first of all, to get you thinking about building this in the future, and secondly, because it had an understandable schematic on it. Anything else?
So when it refers to the programmer, I always get confused what exactly it is.
It is a device that takes a hex code, a compiled code as input, a memory image as input, and downloads it to the microcontroller proper.
Is that the hex code? Is that usually come from the computer?
So there's a cross compiler that runs on the PC called AVR Studio, and WinAVR GCC, that takes C code source and produces a hex file as a memory image. And then the programmer takes the memory image and downloads it to flash memory on the microcontroller.
So is that kind of piece of kind of actual hardware?
Yes, it's actual hardware.
And usually,
It's on the STK500,
okay.
but for the prototype board, it is a separate module.
Okay.
We have a box full of these little blue boxes that do the protocol conversion.
Okay, sure, thanks.
So I think I was halfway through timing demo code. So last time we talked about the interrupt service routine and main and initializing all the ports and timers and so on. Any questions about that? I'm going to finish that up today. We did all the low-level stuff. The only thing we didn't do is to write out the 3 tasks that we're going to blink LEDs and check for button pushes. And the reason they're separated into 3 tasks is more pedagogical in this case, but the button push routine runs about every 60 milliseconds, because if you go much slower than 60 milliseconds, a button push starts to feel draggy or laggy. You can detect something on the order of 50 or 60 millisecond delays. If you're really into animation and synchronizing sound with video, you're probably good down to 10 milliseconds or slow. So if you've been practicing. But most people probably don't practice that, do you? Anyways, 10 milliseconds is too fast. 60 is about as slow as you can go. So let's write task 1 out. And if you will recall from last time, task 1 is going to blink a light at either 2 per second or 8 per second. And main, which is acting as kind of the world's stupidest scheduler, is scheduling task 1 by reloading a timer with the value of 250 milliseconds, I think. Yes, 250 milliseconds. And as usual, we'll use begin rather than curly bracket. And the way we're going to speed up the blinking is we're going to check for this message from task 3, TSK3 message, and ask, is this not equal to 0? And if it is, we're just going to speed up the blinking by causing this routine to reschedule itself earlier. So that's the weird C notation, as you probably know, for a shift by 2 bits. That's a divide by 4. And so the reschedule time has been dropped by a factor of 4, and so we go from 2 hertz to 8 hertz. So then we're going to toggle the low order bit of the LED variable. So we're going to XOR it with 1. And remember that unlike in MATLAB, that's not power, that's XOR. That gets me all the time. And then we're going to copy the LED variable to port B. And just for grins here, to exercise the serial function, we're going to do an F print F to standard out, which is the terminal, with this cryptic string %D \n\r end quote, and then the running time variable, which is time since reset, and then we're going to end. The fprintf assumes that you have a PuTTY-like terminal, a terminal emulator running on the PC, which is attached to the board with a USB to serial dongle. The CPUs we have currently in the lab have one serial port, hardware serial port on the back. I strongly suggest that you hook that to the programmer. The programmer on the STK500s uses a serial connection to the CPU. The TAs will have set up an example of how this works for your first lab. The other channel that you need, the other serial channel you need, will have to be through a USB to serial conversion. Unfortunately, we have 4 different kinds of serial dongles, because every year we buy more because something happens to them. I don't think people steal them, because who wants a serial dongle anyway? But they just kind of evaporate. In any case, we have 4 different versions, and only one version was recognized by Windows 7. So you have to download the driver for the other ones. You're all going to be running as administrator in the lab. And before you get any crazy ideas, we're running with so-called deep freeze. You know what that is? Every time you log off, it wipes everything you've done completely off the machine. You can delete the operating system. And when you log off or cycle the power, it'll be back. So every time you log in, you'll have to reload the driver until the system load lightens up enough that that our administrator can install the other stuff.
Can you go those inputs to fprint?
Fprint, oh sure. FPRINT, yes. Okay, the first input is the is the unit you're outputting to. Standard out is what was defined in the UART initialization file definition as the print unit. Then this %D \n\r. %D says take the first parameter in the list after the current parameter, convert it to a decimal integer, and format it. Then \n\r means new line and return, which would now be called enter. But back in the days when you did a carriage return on a typewriter, you hit a lever and pushed the paper back across so that you could type. That's why it's called return. And then time plus plus is the running time since the system was reset, and time plus plus means read the value, evaluate it, then increment it. So this reads the value, then increments it for next time.
So it's incremented with the display, or it's incremented with everything?
Oh, it changes the variable. It changes memory.
Do you need to reset TSK3M to 0 anywhere?
In task 3.
Okay. So I'm just worried about time 1 getting shifted by 2 every time thereafter.
Oh, but you want it to be, because every time this executes, time 1 has been reloaded with 250 milliseconds.
Okay. Yeah, I see.
Yeah.
So it's outputting the time plus plus for the incremented time. That's
It's-
what you're actually outputting.
You're incrementing the time, and then you're outputting the time, and then incrementing. If we'd said plus plus time, it would have incremented and then output it. These are these weird C operators. Like, you know, like this ugly thing that does the shift and replacement all in one operator. This is equivalent, I guess I should write this out. This is equivalent to time 1 equals time 1 shift 2. And this is one reason they call C a write-only language. Have any ever looked at the obfuscated C contests, where you make it as hard as possible to read the program? It's awesome. Look it up. These things are incomprehensible. I saw a basic interpreter written in C, but it was all one line. Okay. So now we have task 2, and you remember task 2 is just ticking along, flashing an LED once per second, but because I'm using byte variables, I had to do a count to get to the appropriate number of milliseconds. So if we take the decremented value of the task 2C, and here we're pre-decrementing before we do the compare, equals 0, then we are going to set the task 2 counter back to 4. I think that the temperature has been set up in here again. I feel suddenly, no, I guess I'm just took too much niacin or something. Having a hot flash. So LED is equal to LED, and then we're going to XOR this with 0x02 bit 1. I'll put this to port B. And end. So this is just going to count up in the, if I remember right, task time 2 was set to 125 milliseconds. And so counting to 125 4 times will give us 500 milliseconds for a cycle time of 1 second. Task 3 then is just going to be really embarrassingly simple. Task 3 M is equal to not pin D and 0x80, so that we're detecting only bit 7. And because the push buttons on the STK500 are inverted logic, when you push them they become a 0, it's easier for me to think about it if I just automatically invert them before I do anything about them with them, so that it becomes positive logic.
Why isn't time 2 just 500?
Can't be 500 because I use byte variables. And the maximum size for a byte variable is 255. So if I bothered to recode this from the assembly language using integers rather than bytes, I could have done it directly. Now, as I said, this is a little bit granular. It doesn't seem hardly worthwhile to put this in a separate task, but it was useful for showing how to schedule different functions at different time intervals. Any other questions about the code?
So does that mean it's detecting the D8 push button? Is that?
The 7th push button. It's 0 based.
Oh yeah. So the 7th push button, and the way we can detect on pin D is that because we wire that push button to
Port D.
right?
That's correct. Yes.
So it, okay, I see.
Yeah. D7 I think is pin 21. I think. Might be 22. On the STK500, as you may know from the pictures in the lab, the photographs in the lab, each port is brought out onto a 10-pin connector in which we have bits 0, 1, 2, 3, 4, 5, 6, 7 ground VCC. So there's a 10-pin connector on the board that carries 8 signals plus ground in VCC. And we have these very nice custom-made 18-inch gray cables that snap onto these headers and end in a P-dip connector on the other end, which fits nicely into the whiteboard. So you can bring the whole cable, the whole port, all 8 bits over to the whiteboard with one connection. And the nicest thing about them is you can leave them connected to the whiteboard from lab to lab, so you don't have to rewire this stuff every time. So you can unplug them from the STK500, wrap them around the whiteboard, put them up on the shelf, and keep them. If you wire it any other way, you have to take it apart. If you use the point-to-point wires that we have, you have to take it apart. Okay, so there's a couple of details left. One is, what is this LCD thing that we're going to be using? The LCD displays we are going to be using are themselves CPUs that run an internal state machine, and your program has to coordinate with and command the state machine running on the LCD display. It's not a raw segment display, but rather you give it high-level commands like erase or draw a character or go to 4-bit interface or 8-bit interface mode or a dozen other things but you probably should not waste the time to actually read the LCD data sheet, because it will give you vastly more detail than you ever want to know right now. What you do need to know is that there's going to be one port that connects the connects the microcontroller to the LCD, and seven pins of the port will be used. So if we lay this out as LCD pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, oh dear, 11, 12, 13, 14, 15, 16. Not all of the LCDs we have pins 15 and 16, but if they do, you don't want to connect anything to them. So these are no connects. Pin 1 on the LCD, it's a little board, is almost always, not quite almost always, but almost always the pin which is nearest the corner of the physical package. So the thing looks like this, with a connector up here and the LCD display here, and this is almost always 1. But every single package has it numbered. So you look at the back of this thing, you look at the printed circuit board side of this, and you look for the number 1 before you start wiring. Pin 1 takes ground. Pin 2 takes VCC. Pin 3 is the output of a potentiometer hooked between 1 and 2. It's a 3-lead device, trim pot. If you wire this up incorrectly, which I've seen many times, you blow up the trim pot. First time, boom. So read the lab page moderately carefully before you hook up the trim pot, because we got a lot of them in the drawer that aren't trim pots anymore. Oh, this one doesn't work. Oh, I'll get another one. Oh, this one doesn't work. Yeah. This is going to go to, let's say we're going to use port C, C.0, C.1, C.2. 7 through 10 is no connect. C.4, C.5, C.6, C.7. You can use any port you want, except don't use port B. The reason for not using port B is that the CPU is programmed through port B, actually B, 5, 6, and 7, which happens to be the data bus. So, if you happen to interrupt the operation of the LCD during a read operation, then the LCD will be driving the bus, and the programmer cannot program the chip. And you'll get a program failure. And then you'll ask the TA, what's wrong? Don't hook the LCD to port B. If you do, if for some reason you decide you just have to, then every time you program, you're going to have to unplug it, program, and plug it back in. It's not the end of the world, but why bother? I did skip C.3 because it's not connected. C.3 is not used. Thank you.
Since here we are using POC to drive the LCD, should we also do the initialization for the POC in the initialize?
Oh yes, you have to do that. I'll show you how to do that.
But it's not included on last lectures,
No, but I'll bet you can guess how to do it.
Okay.
But yes, I will show you how to do that in either today or next time.
Okay.
The LCD code initialize. There's an LCD test code that initializes the port correctly. There was a question. It's for the LCD. It's not used for the LCD because it's a 4-bit data bus, 3 control lines. No, port C3 is a perfectly good port. You can use it for anything you want here. You could blink an LED off of it if you wanted to. So there is an LCD test code. It's written in a embarrassingly bad style. I take credit for that embarrassingly bad style. I haven't rewritten it for a while. But what it does is, on the display, it displays the word number equals here, and then there's a count that occurs for 4 digits. So it counts up just to show that something's changing. And then the number, the letter small o, is made to animate and go back, cross here for 7, then back, and then across and back like that, about every 200 milliseconds. So you get this cheesy animation of this ball moving back and forth. This was pretty much just to show the code was running, right? That I understood how to make the code run. And the first version of this I did back in 1997 was in assembly language, and took about 2 weeks of lectures to explain how to use. It was just horrible. All right, just the interface was just massively ugly. But now it's just a library you call. So it takes maybe half an hour to talk about the. So there are progress in some things. One reason that this code, the main reason that I think this code is ugly, is that it uses the CPU. It uses uses the CPU clock as a delay function. It uses software delay, something which you never will do in this class. Never. First of all, it's bad practice. Secondly, it'll lose you a pile of points. All right. So that's why I have to rewrite it, but I haven't yet. This particular code doesn't include on a util/delay.h. And there are 2 main functions in this: delay underscore millisecond, which takes a parameter, and delay underscore microsecond, which is actually a u and not a mu, which takes a microsecond measure. And you will never use this function. All right? Never. You may use microsecond delay occasionally because it's actually rather hard to get a few microsecond delay using an interrupt. The granularity of the CPU is not quite good enough to get a 16 cycle 1 microsecond interrupt. So this is acceptable and is used in quite a lot of places. This one won't be. However, it is used inside the LCD initialization package by the person who wrote this function, because the person needed a 1 millisecond or 2 millisecond delay in places. Now, how does this thing know what the clock rate is of the CPU? You set it in the programmer. So there's also an environment variable you can set in the program, fcpu I think, which sets it to 16 million. But you must set it. So let's say that you start a new project. You don't set the clock frequency. It defaults to something. Who knows what? The delay millisecond, instead of timing milliseconds, is timing fortnights. And the LCD will never initialize. And so the symptom will be, when you forget to set the clock, the symptom will be either the LCD doesn't initialize or it shows completely random character segments. Just garbage across the screen. And you should immediately say to yourself, I better check the clock. The particular example we're going to use here also stores some strings in Flash. Now, Flash is a relatively large resource on this chip. There's about 64K of Flash. RAM is relatively small at around 4K. And so anytime you can put a large constant string in Flash, you're going to save useful RAM memory space. There is a library which interfaces which gives you a set of utilities for using the program space .h. And this allows you to do things like define a constant int 8t, so this is an abstract form. We're just going to, let's give a LCD string number so the name of the variable, the name of the string, and then use the keyword progmem. Progmem equals, quote, number equals. And you have to terminate it with a \0 because all strings in C are terminated with a 0. We're also going to include std standard io.h standard lib.h standard lib.h. What's in standard lib.h? A couple of fixed to float routines, a random number generator. What else? Huh? No? Probably. Yeah. What else? I can't remember. There's a link. There's a link on the Lab 1 page to the WinAVR GCC AVR Lib, which has all of these functions laid out for you. We're going to include string.h. You can guess what that is. It's string functions of various sorts. And we need to include LCD lib. This one?
Is it constant and yeah?
This is an int 8 underscore t. Just that's the same as saying it's a car. So I can plow through, I'm not going to plow through the rest of this now. It's getting too close to the end. So I suggest you go to Lab 1 and look at the LCT demo code and be ready to talk about that on Wednesday. Wednesday is the first lab. Homework is due on Wednesday or Thursday or Friday, depending on which lab you have. I'll be in all 4 of the labs this week just to make sure everything's set up and running. And I'll be looking forward to it. But we have a couple of minutes here. We got 5 minutes. Let's talk about final projects. It's never too soon. I'm going to encourage you, first of all, to build one of these prototype boards I was talking about for final projects. For a final project. That way you can hack it into your hardware. You can chop the board up. You can do anything you want with it. It's yours. Once you build them, they're of small pedagogical use to me. I'll keep them if you don't want them, but most people take them. Particularly if they've built a video game or something that they want to, take home and show mom what they bought for the year. We will encourage you to put up your project as a web page. You will be required to write it as a web page. I will be happy to help anybody try and get their project into print in a magazine if you are willing and we think that it has a chance of making it into the magazine. We get about 3 projects a year into magazines. We could get twice that many, except students don't bother to write them. It's the end of the semester. I'm out of here. We could get probably, over the past few years, we've gotten about 1 patent disclosure to Cornell per year. I think we could probably get a little bit more. There's been a couple of really good ideas that I thought the students should follow up, and they didn't. One was a fan that tracks people around the room. That's really cool. What a good idea. And I think I've never seen anything like that on the market. I've never even heard anything like that. This thing, it popped out of their brain. So, just, come on, guys, do a disclosure. No. And another one was an instrumentation system that went around bicep and arm so that you held the correct attitude of your arm while you were doing curls. And some weightlifters are pretty nuts, and they'll spend anything for supplements and hardware. So we figured, we could sell this to, they could sell this to weightlifters for form, right? For keeping form while doing bicep curls. And again, I've never seen anything like that. Couldn't get them to write it up. So I'll be happy to help anybody with intellectual property on this. We would encourage all of you to put video up on YouTube of your projects. Now, I brought up a ECE 4760 channel on Friday, and I put up about 20 or 25 old projects on it, and so far I've gotten 9 subscribers. There's somebody in the class with 3 orders of magnitude more subscribers than that. So that's good advertisement for you. It's good advertisement for Cornell. And it's a lot of fun. You get the weirdest comments. Strangest comments. Oh, my kid brother did that in 6th grade. That's my favorite. By far, not by far, one of the most talked about projects ever in this class, which you can look up now on Facebook or on YouTube, is the fart intensity detector. which made Popular Science magazine, a whole page in Popular Science magazine, the print magazine, right? And my administration was not entirely happy with this. How are we known exactly here? Farts and Sciences? Yeah, it was. They couldn't get around the idea that this was really good publicity. Look it up. Interesting set of engineering.